Okay, welcome. This is the first in what will likely be a series of videos introducing a new cryptocurrency called Illium. Illium makes use of some recent advancements in zk-snarks to make all transactions fully private. This doesn't just include basic transfers, as was the case in like Zcash and others and past generations of cryptocurrencies, but we extend it to include all kinds of transactions. We have a Turing-complete scripting language, so there's Turing-complete scripts, token transfers, smart contracts. Everything is done completely in zero knowledge, and so all transactions on layer 1 are fully private, and you really can't tell one from another, right? That a basic transfer looks exactly the same as the world's most complex smart contract when you look at it on a blockchain. So in this video, we're going to talk about the current state of the art in zk-snarks, and in particular, we're going to talk about Lurk, the Lurk programming language, and how we use it in Illium, and we're going to code up some examples. And as you're going to see, it's pretty mind-blowing how far things have come with zk-snarks from when they first came out. So to begin, let's just briefly talk about what are zk-snarks? Essentially, they're programmatic cryptographic proofs that allow us to create a zero-knowledge proof for just about any kind of statement we can write in code. So in this little interface, in a perfect world, we'd have a real thin interface, something that looks like this. And what we would start with is this foobar function. The foobar function, we could name it anything, but it's a function that we would write in code that's going to have some inputs and it's going to produce an output. And basically what we want to prove is that we know some combination of inputs, and these inputs can be private or public. The private inputs would not be revealed to the verifier. Public inputs we can share with the verifier. But we're going to prove that we know some combination of private and public inputs that produce a particular output. Usually it's just like true or false, but it doesn't have to be. It could be an integer, it could be anything in the return value of the function. But we know some combination of inputs that produce a particular output, but we're not going to reveal what those inputs are, or at least not what the private inputs are. We might reveal the public inputs to the verifier, but the private inputs we're not going to reveal. And in a perfect world, you just have a real thin interface that looks something like this and very easy to use. But unfortunately, up to this point, zk-snarks haven't been anywhere close to this easy to use in practice. So let's talk about some of the limitations. When you actually look at what zk-snarks are doing under the hood, is they basically have to be implemented in arithmetic logic, or basically like mathematical statements. So you're not writing in normal Boolean logic, you're not writing normal code. When you create your zk-snark function, you're writing code that kind of looks something like this, like just a bunch of equations, right? And in this example, we've got 10 constraints here. Imagine a program that's doing even something like mildly complex might have like 20,000, 50,000, 100,000 constraints. So imagine trying to write a program that looks like this with like 100,000 of these type of mathematical constraints. You'd pull your hair out trying to write code this way. There have been compilers created that allow us to sort of write in a higher level language and then compile down into all this stuff. But it's still not the same as normal programming. We've got still some big issues. So when it comes to loops, normally when we program like normal, you can break out of a loop anytime that you want. You do a certain number of iterations. Once you've done whatever computation you need to do, you can just exit the loop, and the loop doesn't need to continue. Well, you can't do that in zk-snarks. So if you have a loop, you need to figure out what is going to be the maximum number of iterations through the loop that I might need to do. And then you have to bear that cost every time through the loop. So, if sometimes you need to only make 10 iterations, sometimes you need to make 50, and sometimes you need to make 10,000 iterations, well, then every time you're going to need to make 10,000 iterations through the loop, because this is just the way the arithmetic logic works under the hood. So there's no kind of breaking out of a loop early, if you will, to avoid more expensive computation. Same thing with if and else statements. Normally you have an if block and an else block, and the if block, if the condition is met, the if block is executed and the else block isn't, or vice versa. And so you can, if you have expensive computation in like an else block, normally you can just skip that if the condition's met. In zk-snarks, we're going to have to execute both sides of the if and else block. So you can see computation starts becoming very expensive and kind of very cumbersome and sort of almost like difficult to reason about. And it's certainly very foreign for many developers. So where we are is, in recent years, there's been some big advancements in zk-snarks regarding like recursive snarks, which is sort of the ability of one proof to attest to the validity of another proof, and things like incrementally verifiable computation, which has sort of opened up a new paradigm in how we do zk-snarks and how we use them. And people are able to start creating these things called like a zk-VM, or zero knowledge virtual machine, that is sort of replicating kind of like a programming language or some sort of a programming language under the hood that gets much closer to how we're actually used to programming. So talk a little bit about what this is like. So in computer science, we have this kind of foundational concept of a universal Turing machine. A Turing machine is a hypothetical computer that has the ability to read and write data to some sort of storage medium, and it has some sort of rule set associated with it. And the ability to basically read and write data combined with the rule set allows the Turing machine to basically do some computation and execute a program. And then you have a universal Turing machine, which kind of has the ability to sort of take in a description of another Turing machine and adopt its rule set, allowing the universal Turing machine to basically perform any sort of computation that we would want. And so we kind of want to have a similar type concept as it relates to zk-snarks. If we kind of go back up here, we see this foobar function. I should just kind of mention, in zk-snarks parlance, we call this function a circuit. So if you hear me use the term circuit, this is what we're referring to. But kind of what we would like to have is some way of building sort of a universal circuit that is somewhat analogous to this universal Turing machine. Can we take in a description of a program and then have a circuit that allows us to do the computation and create a proof for any sort of program that we would desire, right? So instead of like compiling down into this, all these constraints like we would do before, we would write our program in some higher level language, compile it into these constraints. What we're looking for is something more analogous to an interpreter, like an interpreted language. So this is kind of the approach that Lurk takes. Lurk is not the only one, but it is one of a handful of these like zero knowledge virtual machines that are kind of competing for market share out there right now. Lurk is probably doing things maybe a little bit more unique compared to some of the other ones. And the approach that Lurk is taking is, it's a little bit of a throwback to this paper here from 1960, Recursive Functions of Symbolic Expressions and Their Computation by Machine, which is from McCarthy, where he's describing the Lisp programming language. And basically what Lisp is sort of a very minimalist, it's a very minimalist programming language that has a very sort of minimal set of rules that allow you to kind of like recursively sort of step through a program to its execution. So what Lurk is essentially a Lisp interpreter inside a circuit. And what happens is your program, when you write your program, it gets broken up into a bunch of chunks. They call them frames in Lurk. And then each frame it becomes an input to the circuit, to one iteration of the circuit. And it's able to, do some computation with it, update an environment, and produce an output. And that output then becomes the input to the next iteration of the circuit, and it kind of describes how to complete the computation this way. So you can basically kind of step through a program this way by having many, many iterations through the circuit until you produce a final succinct zk-snark proof. So an example here of Lurk. This is just an example from the website. This is a program executing a recursive function here that is computing a Fibonacci sequence, and you can see this would be 89 iterations through the circuit. So, there's some looping going on inside this function, which in part accounts for the number of iterations. But basically, this gets us back to sort of normal programming that we're used to. We're back to Boolean logic. Loops work the way we kind of expect them to work. I can break out of a loop at any time. I don't need to compute what is the maximum number of iterations through the loop I would need to do and then bear that cost. If and else statements work the way you would expect them to work, if the conditional is met, the if statement is executed and the else statement isn't, or vice versa. So we basically kind of get back to normal programming. So what I want to do in the rest of this video is just work through some examples of how we use this in Illium and do kind of a little demo here. So I should point out that Lurk is written in Rust, and the interface, there is a little bit of a learning curve to understand the interface and how to use it in Rust. What we've done here in Illium is we've kind of created a wrapper around the Lurk interface to make it sort of almost kind of like a very minimalist interface that's kind of easy to use for our purpose. So what you're seeing here is kind of like our wrapper around Lurk. So just to give some examples of creating some zk-snark proofs, let's start with, we're going to create a program, and this program there's going to be a function, right? This is kind of like that foobar function that we mentioned in that slide. We're going to have our functions going to take in a set of private parameters and public parameters, and then we're going to do some computation and return some value. The value is either going to be true or false, nil representing false in this case. So for now, let's just have it return true, just so we can set this up. So we need to create our private parameters, which I'm just going to set both of these to nil now, private and public parameters. These parameters here are going to get passed into our function. So quite literally, this nil is going to get passed into here when our function executes. Same thing with this one here is going to get passed in there. So we have our private and public parameters. We have to create the proof. We use our program, private parameters, public parameters, right? And there's our proof. Okay, and then on the verifier side, what we would send to the verifier is the verifier needs the program. He can, maybe the prover and verifier have prior agreement on the program, or the prover sends it to him, however you want to do it for your use case. He needs the public parameters, and he just needs the proof. So notice the private parameters are not sent to the verifier, only the public parameters are. Okay. So let's give it a run. Okay, there we go. Here's our proof. and it returned true, and we have a valid proof. Now, we didn't actually prove anything, right? Our function just simply returned true and didn't do any actual computation. We're going to change that now. Just kind of a quick note here. Whenever your program starts up for the very first time, Lurk needs to load some parameters from disk into memory, and that can take like a couple seconds or two. So whenever I run this, what you're seeing is it's loading those parameters from disk. So if it takes a little bit longer, it's because than you might expect, it's because it's loading those parameters from disk. Normally for your program, you're only going to do that once, and you're going to do it at startup. The way I'm just doing that here with just executing this test in Go, it's gonna, every time I run the test, it's gonna reload those public parameters from disk. So just a little note as to what's going on under the hood here. But you can see how we basically have that same thin interface that we talked about, in our slides. I mean, look how simple all of this is. So let's say we want to do something a little bit more useful. For example, I don't know, maybe we have a hash function. And I don't know, I want to hash a string called open sesame. So maybe I want to prove, as the prover, I want to prove that I know the pre-image to this hash without revealing what that pre-image is. So the pre-image here is open sesame. Then we have the hash. We'll make the hash will be the public parameter. Okay, so there's our hash. And then the private parameter will be the string. Right? So we can run this. Oop. Okay. It would be nice if I actually did program the body of the function. Okay, so let's do that. I forgot something here. So what we want to do is we want to, inside our function, we want to check that the hash of our private value, which is the string, and the keyword for the hash function in Lurk is commit. It uses the Poseidon hash function. So we just want to check that the hash of the private value is equal to the public value. And then just one other thing is, in order to check the equality, the types have to be equal, and I'm just going to cast this to a number type. So there we go. Now we can run it. Okay, so there we go. So here's our proof. It's valid. So let's just recap what we've done here. As the prover, our private parameters are the string that we're hashing. It's our pre-image. And we're not sending that to the verifier, right? The verifier only knows the hash. And so we're proving to the verifier that we know this password, essentially, without revealing what the password is to the verifier, okay? In this case, I mean, this password might be easy to brute force, but, if it was longer and more random, then, the verifier would not be able to figure that out. Okay, so we've proved that we know the pre-image in zero knowledge, essentially, right? So you can think of all sorts of things that maybe you could do with this. Like, for example, maybe I want to prove to someone that I'm like older than 18, for example, but I don't want to tell them my actual birthday. Okay, so how might we go about doing this? We could make our private parameter, I want to have a birthday. I'm just going to grab a Unix timestamp here. Okay, so we'll make our private parameter as our birthday. Okay, so priv will be our birthday. This is the birthday in seconds since the Unix epoch. And then we want to check that we are older than 18. So let's do okay, that's the number of seconds in 18 years. So maybe we'll check. So we'll check that the private parameter, which is our birthday, is less than the public parameter, which we'll pass in, will be the current timestamp. It'll be the current time minus 18 years. Okay, looks good. And then our public parameter is just going to be time.now. All right, give it a run. Okay, so again, our proof is valid. So again, just to sort of recap what we've done here is we've proved that our birthday, or that this birthday that we entered is has us, older than 18 years old, or essentially that our birthday is less than time.now minus 18 years, which is proving that we're older than 18 years old. And we've done this without revealing our birthday to the verifier. Okay, so the private parameter is our birthday, and we don't reveal that to the verifier. We just give the verifier the current timestamp, the current Unix timestamp, and as the public parameter. So I don't know, maybe we want to increase the complexity of this a little bit. In this instance, our birthday, we're just entering the prover's just entering any birthday, and you could just be entering any birthday and not his real birthday. So maybe, I don't know, imagine there's some sort of third party, like an Oracle or something, that is a test to somebody's birthday who has maybe signed the person's birthday and is attesting to that it's his real birthday. And maybe we want to check that signature. So let's see how we might do that. So imagine we have an Oracle that has a private key, public key, let's set our birthday as a byte array or byte slice. Okay, and then we're going to sign, the Oracle is going to sign our birthday. Okay, and then what we want to do is we want to verify the signature inside the circuit, or inside our function here, in addition to verifying that our birthday is correct. So the way we're going to set this up, we need to use some macros here. So let me do I'm going to import the checksig function. Let's define some variables. We'll set our birthday. So we'll make priv and puv, instead of just expressions, we'll make them lists. So we'll set our birthday equal to the first value in the private list. And we'll have the signature be all the other values. We'll pass in our timestamp, time.now. That'll be the first value of the public parameter. And then the oracle's public key will be all the rest. Okay, and so this would change our function here. So it would be if our birthday is less than now minus 18 years, then we want to execute the check_sig function, checking the sig covering the birthday. Otherwise, we just want to return nil. And I think that's everything. So this is going to be a list with the birthday is going to be our first variable. The sig will be our second, but these Lurk programs are defined over a finite field, which means that variables can't be larger than the maximum field element. So in this case, our signature is larger than that max field element, so we have to kind of break the signature up into its components that will fit within the field, which is the x and y coordinates for the r value and then the s value. And then we'll pass those in as our private parameters. Okay, our public parameters will be we can just make it our time.now will be our first value, and then same thing with the public key is going to be the second value of the public parameter right here. But we have the same issue where this public key doesn't fit within the field element, so we have to break the public key up into its x and y coordinates. So okay, everything looks good. One final thing is these macros are not part of Lurk proper. They're essentially extra stuff that we've added for Illium just to kind of make it a little bit easier to code. So before we pass the program in here, we just have to expand the macros. So let me create a preprocessor. Okay, so let's just double check and make sure everything looks right. Birthday is less than time.now. All right, let's give it a run, see what happens. All right, voila. So let's just recap what we've done here. We are proving in zero knowledge that we are 18 years old, and we're proving it by passing our birthday in as a private parameter, but we're also verifying in zero knowledge a oracle or a third-party signature covering our birthday and proving that this third party is attesting to that our birthday actually is correct, and we're just not entering any random value in there. The private parameters are, again, our birthday and the signature. That gets passed into the proof function. The verifier only gets the public parameters, which is just the current timestamp, and then the public key of the oracle, and then he knows the program as well. Okay, so I mean, basically, if you've ever done any kind of programming with zk-snarks in the past, like this is unbelievably simple compared to how it used to be. And this simplicity and this kind of programmability in zk-snarks, it's basically just available like right now. Okay, that this hasn't been possible really very much in, going back not far at all. Like this is pretty much the first time that we've been able to make zk-snarks this simple to use and make it like normal programming. And so this is a big hat tip to the Lurk team for making it this easy. In future videos, we'll probably talk about how specifically we use Lurk in Illium. For example, we could just take a look at some of these. Like we have a multi-sig script here. This is a locking script that allows us to do multi-sig. If you want to see like the Lurk program that we use to validate transactions on the network, this is what it looks like here. So just to kind of recap, we've gone from how zk-snarks, the complexity of those zk-snarks having to use arithmetic logic instead of Boolean logic and all these issues with loops and just the overall complexity, now to something that is very easy for developers to work with. And this is part and parcel what enables us to do smart contracts and scripting. This is, I should point out, Lurk is a Turing complete language. So pretty much anything we can write in code, we can do in this, and we can validate all of this in our transactions here in Illium. So that's it for now, and thanks for watching.